In this lesson, the electrochemical cell potential difference in a voltaic cell is related to the concentrations of the aqueous ions in each of the half cells. This can be shown for any voltaic cell, but was first quantified by Nernst using a zinc-copper voltaic cell. At the anode, Nernst used zinc and the cathode was the copper, and that yielded the net reaction of zinc oxidized to zinc 2 cations and the copper 2 cations reduced to copper. For that redox equation as written, there are 2 moles of electrons exchanged per mole of reaction, as can be seen by the half reaction method. Q, the reaction quotient, is whatever the concentration of the products are at a given moment divided by the concentration of the reactants. Both from the equation are to the first power, and the solids do not show up in the Q expression. So what Nernst did was, at a given temperature for this voltaic cell, vary the concentrations of the zinc cations and the copper 2 cations, starting under standard conditions of 1 molar, and recorded the electrochemical potential difference initially, which is the maximum reading, and Nernst observed 1.10 joules per coulomb or volts potential difference between the anode and the cathode given those 1 molar concentrations. What he then did was vary the relative concentrations of the zinc and copper aqueous cations, and noticed that there was a difference in attraction between the 2 half cells, yielding a different electrochemical cell potential difference. When Nernst relatively increased the concentration of the reactant cations, the copper 2 plus, and decreased the relative concentration of the zinc cations, he noticed that the initial cell potential difference was greater. So for the lesser zinc concentration divided by the greater copper concentration, in other words a decrease in Q, he noticed that the cell potential difference increased. In order to linearize the data, he had to take the log or the natural log of that reaction quotient, and that ended up linearizing the plot. So we noticed this relationship: the lower the log or natural log of Q, the higher the cell potential difference. What's going on kinetically there, by increasing the concentration of copper relative to standard conditions and decreasing the concentration of zinc cations relative to initial standard conditions, he basically sped up the rate of the forward reaction, because there was an increase in the copper 2 plus cation concentration initially, and he slowed down the reverse reaction by decreasing one of the products, the one that could alter in concentration, the zinc cation concentration. So relative to standard conditions, when there is a faster forward reaction rate and a slower reverse reaction rate, that's reflected with a greater difference in attraction for electrons between the half cells, and the cell potential difference increases. When the opposite was tried, loading up on the product concentration, the zinc 2 plus aqueous, and decreasing the reactant concentration, the one that could be altered, the copper 2 plus, that increases the reaction quotient. It increases relative to standard conditions the reverse rate of reaction compared to the forward, and he noted a lower and lower cell potential difference, a lower and lower difference in attraction for electrons between the 2 cells. So this linear relationship between the cell potential difference and the log or natural log of the reaction quotient, with a y-intercept at the x equals 0 point where the y-axis begins, of the standard cell potential, later became known as the Nernst equation. And that could be used for any concentration of the reactants or products that can be manipulated in the reaction quotient. So under non-standard conditions, given the standard cell potential difference noted, one can compute or calculate without even doing the experiment under ideal solution conditions what the cell potential difference will be. And this is a perfectly logical result of kinetics, and is sometimes asked for in terms of the not really explaining anything Le Chatelet principle. We can see what happens to the variables in this equation at equilibrium, where there is zero cell potential difference because the forward and reverse rates of reactions are equal, and there's the same net attraction for electrons between the half cells. So E cell becomes 0 volts, and the right side of the equation we can then rearrange to the standard cell potential difference. Q turns into K at equilibrium. So there's a relationship between the standard cell potential difference for a given reaction and K, the equilibrium constant for that reaction at a given temperature T. Because, as you know, temperature is the only variable that affects the value of the equilibrium constant. Therefore, it's the only variable that can affect the standard cell potential difference. And further, the relationship between the cell standard potential difference and the standard Gibbs free energy change for the same reaction allows for that third relationship, negative delta G standard for the reaction divided by NF. And again, N is the number of moles of electrons exchanged in the balanced equation as written per mole of reaction as written. Typically the Nernst equation is written in the non-graphical form, where you put the standard cell potential difference first, but if you're given a graphical question, typically you write it based on what is seen on the graph, with the mx plus b part written in that order.